Today I will be presenting Lab 5, which is on Faraday's Law. Now for an overview of Lab 5. Some of the key fundamental concepts applied in Lab 5 include Faraday's Law, which states that a moving magnetic field will induce a current. We'll use Faraday's Law to find the current on each ring of our aluminum foil tube. Another key concept we will use is the Biot-Savart Law. We will use this to find the magnetic force from the tube on the magnet. And the last key concept is Newton's second law, F equals ma, which will help us to account for the adjusting position and velocity of the bar magnet. The main objectives for this lab include visualizing and recording the interaction of the bar magnet falling through the tube, creating a computational model of the bar magnet falling through the tube, and comparing the results from our experiment and the computational model. Before conducting the experimental portion of the lab, I needed to identify the north and south poles of the bar magnet. First, I positioned the Teslameter to account for magnetic north. I then moved the bar magnet towards the Teslameter. By visualizing which side of the magnet led to a positive increase in magnetic field, I was able to determine the north and south poles for the magnet. Supplies needed for this lab included the bar magnet, an aluminum foil roll, a meter stick, and a video recorder. After identifying the north and south poles, drop the bar magnet through the aluminum foil tube and record this process. I dropped the bar magnet with the north pole on the bottom and the south pole on the top. Then looking at your video, identify the time when the bar magnet entered the aluminum foil tube and the time when the bar magnet exited the aluminum foil tube. Subtract these two values and record that, and repeat this procedure 5 times. Here are my results from Lab 5. I got an average time of 0.95 seconds. I noticed that the bar magnet moves much slower through the tube compared to free falling, and the magnet rotated slightly as it fell through the tube. I will now go through the steps of Lab 5 coding. Step 1 was to add the geometric parameters of the aluminum foil tube. I also included the value for the bar magnetic moment, which I obtained in Lab 3, and the mass of my bar magnet. The next step is to create a function for calculating the magnetic field of the magnet. I used the function I used in Lab 3. The line with the gray arrow pointing to it indicates where the Biot-Savart law is applied. The next step is to create a function to calculate the change in flux over time through each ring due to the falling magnet. For this function, I implemented Faraday's law. I then created a gravitational force vector by multiplying the mass of the magnet by the gravitational constant. Moving on, I wrote code to compute the current in each ring. For this, I called back on the change in flux over time function. Then, using the Biot-Savart law, I wrote code to calculate the magnetic force acting on the ring and the bar magnet. For the final segment of my code, I wrote code to calculate the net force acting on the magnet. Using translational kinematics, I wrote code to compute the changing velocity and position of my bar magnet. Here's a screen recording of my computational model being run. As the magnet falls down, the change in flux increases downwards. In effect, the induced current opposes this change in flux. This leads to a counterclockwise current. As the bar magnet flips, the change in flux reverses direction. In effect, the current changes direction to clockwise. Based on this, the blue ring represents clockwise current and the red ring represents counterclockwise current. The magnitude of the current corresponds to the intensity of the color of the ring. Here's the graph of velocity over time. The velocity initially decreases, then rises to a constant velocity. This indicates that at this point in time, the net force on the magnet is 0. And then the velocity finally drops again. The time I got from my computational model was 7.408 seconds, which is much greater than the time I got from my experimental portion. This could be accounted for by the large magnetic dipole moment or the fact that the model treats the aluminum tube as a solid tube rather than layered sheets of aluminum foil. Now it's time to answer the Lab 5 follow-up questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Ohm's law states that current is inversely proportional to resistivity. A decrease in resistivity would lead to an increase in the induced currents. In effect, the magnet would take a much longer time to fall. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Holes would lead to a decrease in the magnitude of induced currents. Therefore, the magnetic force acting on the bar magnet would be weaker. This would result in the magnet falling much faster. Thank you for listening to my Lab 5 video. Hope you enjoyed.